Good morning, my name is Jorge Bulnes, and today I'll talk about learned index structures. So what is a learned index structure? It's basically a technique using machine learning ranging from the deep neural networks to simple regression in order to model cumulative distribution functions of a sorted array. This is done with the purpose of enhancing or replacing traditional index structures. But why replace it? By replacing branch-heavy index structures like B-trees, hash maps, or Bloom filters with these neural networks, databases, and other systems that can benefit these hardwares. It is important that we understand that we don't want to completely replace these traditional index structures, but to actually add upon them. It is important that we take this approach to build indexes which complements the existing work, and that arguably it opens up new researches and new forms to be more efficient and faster in the process. So for the range index, so one comparison I like to do is between the B index tree and the learn index key. We could compare the other ones, but due to time constraint, I'm gonna compare these. So if you see the B trees have a key, they predict the location of a value within a key sorted set. And we can see that this B tree index has an analytics memory database. In this case, the B tree provides a mapping from the lookup key to a position inside the sorted array of records with the guarantee that the key of the record at that position is the first key equal or higher that looks up the key. The data has to be sorted to allow for efficient range requests. At first sight, we may see that it's hard to provide the same guarantees with other types of machine learning models, but it's actually really simple that the B tree only provides the strong minimum and maximum error guarantee over the stored keys, not for all possible keys, but for new data B trees that needs to be rebalanced, or in machine learning terminology, retrain. So for these monolithic models, we can see in the other side that what we need to do is execute the model for every key and remember the worst over the under prediction of a position to calculate the minimum and maximum error. More importantly, the strong error bounds are not really needed. The data has to be sorted anyway to support the range request, so any error is easily corrected by a local search around the prediction. And thus, we can see that non-monolithic models consequently will be able to replace the B-tree with any other type of regression model, including linear regression or neural nets. So here, on this comparison, we can see the integer data sets. We can see that the size is generally smaller when it comes to the learn index compared to the B-trees. The map data, you can see the comparison. The lookup is faster when it comes to the learn index, and the model prediction is similarly at the same level, is on par. With the web data, you will see a similar approach, and same with the log normal data. So we've shown these learn indexes that they can provide significant benefits by utilizing the distribution of data being indexed. It is important that we emphasize that the learn indexes will help build upon the wide range of machine learning and indexing techniques, especially in B-trees and the variants that it has, such as hash function for artificial neural networks, or perfect hashing, or even Bloom filters. Here we have a conclusion. So for the conclusion, we can see that these data that we found help us understand that we don't want to replace the technology, but we want to build upon the technology. By using these techniques, we can make data go faster, be more cost efficient and overall efficient, and we can discover and develop new researches. Thank you.